The open tube manometer is a U-shaped tube that is filled with a liquid and is used to measure the pressure of a gas. One leg of the tube is connected to the gas tank, or source whose pressure is to be measured. The other leg is open to the atmosphere. According to Pascal's law, the pressure at points A and B that are located at the same elevation is identical. Since the gas density is relatively lower, we can neglect the pressure due to the weight of the column of gas above point A. With this assumption, the pressure at point A is equal to the gas pressure inside the tank. The pressure at point B is equal to the atmospheric pressure that is acting on the open column, plus the pressure due to the weight of the column of liquid above point B, which is equal to the liquid density times the gravitational acceleration times the height of the liquid column h. By setting the expressions for the pressure at point A and B equal to each other, we get the shown expression: P gas is equal to P atmosphere plus OL times G times H. Hence, knowing the atmospheric pressure, the density of the liquid in the barometer, and the height difference between the two manometer legs, we can measure the pressure in the gas tank. Consider the shown experiment, where we can vary the ratio of the pressure of the gas in the tank to the atmospheric pressure. The range of variation in the pressure ratio for this experiment is from 0 to 2. We can rearrange the equation we obtained in the previous section to get H as a function of the following variables: the gas pressure, the atmospheric pressure, and density of the liquid. By multiplying the right-hand side by the atmospheric pressure and dividing it by the atmospheric pressure, we can get an expression of H as a function of the ratio of the gas pressure to the atmospheric pressure. Assuming the liquid in the manometer tube is mercury, we can then substitute 101,300 for the value of the atmospheric pressure, 13,600 for the density of mercury, and 9.8 for the gravitational acceleration, to get the shown equation for H, which now only depends on the value of the ratio of P gas to P atmosphere. 2 points are of special interest here. When the pressure ratio is equal to 0, which means that the gas pressure is 0, we plug 0 into the equation and find that H is equal to negative 0.76 meters. In other words, at a pressure ratio of 0, the manometer acts just like a barometer. On the other hand, when the gas pressure is equal to the atmospheric pressure, their ratio is equal to 1, and plugging 1 into the equation, we find that H is equal to 0. Use the slider to vary the value of the ratio of the pressure of the gas in the tank to the atmospheric pressure, and see how this affects the height difference between the two sides of the manometer's tube. When you wish to continue with the lecture, please press the play button. An open tube manometer that has a diameter of 1 centimeter is connected to a large gas tank. The manometer contains the fluid of an unknown density. 7.854 grams of water are poured into the open leg of the manometer. The pressure in the gas tank is equal to 1.1 atmospheres. If the level of water in the open manometer leg is higher by 30 centimeters than the level of the liquid in the manometer leg connected to the tank, then what is the density of the manometer's liquid? We are given that the gas pressure within the tank is equal to 1.1 atmospheres, or 111,430 Pascal, and that the mass of water in the open leg of the manometer column is equal to 0.00785 kilograms. The diameter of the manometer tube is equal to 0.01 meters, and the total height difference between the surface of the water in the open leg of the manometer and the surface of the unknown liquid in the leg that is connected to the gas tank is equal to 0.3 meters. And we know that the density of water is equal to 1,000 kilograms per meter cubed. We can start by calculating the height of the water, HW, in the open leg of the manometer. We can then use this information to calculate HL, the height difference between the unknown liquid within the open leg of the manometer, and the unknown liquid in the lead of the manometer that is connected to the gas tank. The total volume of water in the open leg of the manometer is equal to pi times the diameter of the manometer leg squared divided by 4 times the height of water. That same volume of water is also equal to the mass of the water in the open leg of the manometer divided by the density of water. Rearranging the equation and substituting the values of the variables, we get the height of the water in the open leg of the manometer to be equal to 4 times 0.007854 divided by 3.14159 times 0.01 squared times 1000, which is equal to 0.1 meters. We can now calculate the difference between the height of the unknown liquid in the open leg of the manometer and in the lead of the manometer that is connected to the tank. That height difference, or HL, is equal to the total height difference between the surface of the water in the open leg of the manometer and the surface of the unknown liquid in the lead that is connected to the gas tank, minus the height of the water in the open leg of the manometer. By substituting 0.3 for H and 0.1 for HW, we get the height difference in the unknown liquid to be equal to 0.2 meters. Using Pascal's law, we can state that the pressure at point A, which is located at the surface of the liquid column in the lead of the manometer that is connected to the gas tank, is equal to the pressure at point B that is at the same elevation, but is located in the open leg of the manometer. Neglecting the small pressure exerted by the weight of the gas column in the manometer tube above point A, the pressure at point B is simply equal to the gas pressure in the tank. The pressure at point B is equal to the atmospheric pressure plus the pressure due to the column of unknown liquid above point B, which is ρW times G times HW, plus the pressure due to the column of water above point B, which is ρL times G times HL. Equating the expression for the pressure at point A to the expression for the pressure at point B, we get the shown equation. By rearranging the terms, we can get the shown equation for the density of the unknown liquid. We can then substitute the values of the different variables. 0.24 HL, which we calculated in part 1 of our solution. 0.14 HW, which we also calculated in part 1 of our solution. And then the other variables that we were given. 111,430 for P gas, 101,300 for P atmosphere, 9.81 for G, and 1,000 for ρW, and we get that the unknown density is equal to 4,663.1 kilograms per meter cubed. An inclined manometer is used for measuring small gas pressures. Compared to a U-tube manometer, the inclined tube manometer offers a better accuracy in reading small pressure changes. This is due to the fact that a height difference, H, in a U-tube manometer is manifested as a longer length, L, along the inclined tube of an inclined tube manometer, where L is equal to H divided by the sine of the inclination angle theta. For example, if theta is equal to 30 degrees, L would be equal to twice the height difference for a U-tube manometer that is subjected to the same pressure difference. This means that when theta is 30 degrees, an inclined tube manometer is twice as accurate in measuring pressure differences as a U-tube manometer. Of course, the main disadvantage of the inclined tube manometer is that a longer tube is needed to measure the same pressure difference as a U-tube manometer.